This is my second example of how to find the asymptotes of a function given its equation. I'm going to look at the function g defined by g of x equals x plus 2 plus 1 over e to the x squared plus 1. This function has one asymptote, but it is neither vertical nor horizontal. I invite you to pause the video and try to find it. Think about what does the graph of this function look like as x approaches infinity. After that, continue watching. The first thing I notice for this function is that the domain is all the reals, is defined for all real numbers. I have here a quotient, but exponentials are always positive, so this plus 1 is always also positive and never vanishes. So this is always defined, and also this function is continuous in its domain, which is the reals. Since it's defined and continuous on all of R, it can't possibly have vertical asymptotes. Next, let's see if it has horizontal asymptotes. So I need to calculate the limit as x approaches plus or minus infinity. Well, let's look at this part here. As x approaches infinity or minus infinity, x squared approaches infinity, e to that also approaches infinity, plus 1 doesn't change it. So what I have here is 1 over infinity, which is 0. So this whole term approaches 0 as x approaches infinity, and the same thing happens for minus infinity. So for large values of x or small values of x, the function is pretty much just like x plus 2 and nothing else. In other words, the limit of this function as x goes to infinity is just the limit of this piece, which is infinity, and I guess at minus infinity is also the limit of this piece, which is minus infinity. So there are no horizontal asymptotes. However, in doing this, I have discovered something. I just said that as x goes to plus or minus infinity, this goes to 0. So my function is pretty much just like x plus 2. And x plus 2, or y equals x plus 2, is the equation of a line. So what I'm saying here is that my function is pretty much just a line and something that gets very small at infinity. Another way to write this is that as x approaches infinity, the limit of g of x minus x plus 2 is just this piece, and we said that that limit was 0. And the same thing happens on plus and minus infinity. And now this is the condition to have a slant asymptote, that the difference between the function and the line goes to 0. Specifically, let's think about what this means for the graph. In this axis, I have pre-drawn the line y equals x plus 2. And what I know is that as x goes to infinity, the difference between g and x plus 2 goes to 0. So the graph of g should stay very close to the line for large values of x and also at minus infinity. But I know more. I know that as x goes to infinity, the difference is always positive. We argue it was always positive. So it's going to be, the difference is going to be small and positive. So I know g stays very close to x plus 2 and is likely above. And here also g stays very close to x plus 2 and is likely above. So definitely the distance between the graph of the function and the graph of the line has limit 0 as x goes to infinity. So by definition, we have found a slant asymptote. Finally, what will the rest of the graph look like? Well, I know that the graph is always this line plus something positive. So if I had to guess, I would say maybe it's going to look something like this. But I can't quite be certain. It could also do something more exotic and go up and then down and up and down and something like that. If I wanted to be sure, I should look at the first and second derivative and see what the monotonicity and concavity is. And then with that and the asymptote, I will be able to graph it perfectly well. But what I know for sure is that for large values of x and for small values of x, the graph is staying very close to the line y equals x plus 2.